Hey, good afternoon, everyone. Or, if you're in a location where it's still AM like Rick, good morning. This is the eighth session in a series of lunch and learns. I'm the vice president of the INCOSE-Three River chapters. Our president's Dan Monacher, and he asked me to try to get some of the people that I work with to speak on interesting topics. And I've done one, and like I said, this is section 8. We're really lucky to get some of Rick's time today. Rick's a great guy. He's taught me a lot over the years. And he's going to be talking about increasing your velocity by fixing design debt and, specifically software architecture. But I think, he might touch some other spaces as well. Okay, so now without further ado, Rick, I consider him a good friend. He's taught me so much over the years. Rick is, highly influential. He's written many, many books. I got to be honest, I like to tease Rick a lot, but he's always a joy to work with. From when I was younger and I didn't know a darn thing, he was always patient with me and taught me a lot. It's fun. I think he has a wife that's probably a lot better than he deserves. She's a wonderful person, but I'm happy for Rick that he found her. And again, like he's written papers everywhere. And what I like about Rick, it doesn't matter. He is going to work in areas he's not comfortable with or new areas. He's not one of those guys and, hey, I accomplished a few things and now I'm going to sit on my hands for the rest of my life. And so again, without further ado, I introduce you to Rick and turn it over to him. And I know this is going to be a good talk. Rick, it's all yours, buddy.
Thanks a lot, Phil. Appreciate it. I'm going to be talking about the research that has been occupying my time and attention for the last decade or so. Let's see, can you see my slides? Good, all right. And this is on tools and strategies to identify, quantify, and fix design debt, architecture debt. I'll define that in a minute, but this is something that has been increasingly a focus of my research career is trying to analyze architectures and to analyze them with tools and automated means. So some of you may have heard of the ATAM, the Architecture Trade-off Analysis Method, which is a method that I co-authored more than 20 years ago. And ATAM was great, but it required a lot of expertise to be able to run that method. And it wasn't clear whether two people doing two ATAMs on the same system would end up with the same results. So I was looking for something that was more scientifically rigorous and automatable. And that's what I'm going to be talking to you guys about today. And in case you're wondering, the guy on the left of this slide, this is a picture of the myth of Sisyphus. If you don't know who Sisyphus was, he was a Greek king who angered the gods. And as a result of this, he cheated death. And as a result of this, he was condemned by Hades to push an enormous rock uphill every day, only to have it roll back down again at the end of the day. And this is my impression of what it is that software maintainers do every day, that they're working as hard as they can, but they're really never making any progress. The system isn't getting better. In fact, it's probably getting worse. So to give another analogy, this is my view of the state of practice of software development. This poor guy is rowing as hard as he can. He's working as hard as he can. He's probably making some forward progress, but not a lot. And so it's a lot of effort for a small amount of gain. And the question is, why? The boat's leaking, but you keep paddling. And as I say, I consider this to be the state of the practice in software development. I've analyzed hundreds and hundreds of open source and commercial projects over the last decade. And I see very few projects that are not burdened by technical debt, in particular by design debt. So why do we do this? One is the illusion of progress. Yeah, you are moving the boat forward a little bit. You are swatting a bug. You are adding a new feature, but it's harder, right? That requires more effort, more lines of code, more time as the project evolves. And I think that the problem here is the lack of measurements. Architecture is largely invisible to most people. The consequences of bad architectural decisions are largely invisible. And that's what I hope to make visible via my work. So what are architecture or design flaws? Well, you've all experienced them if you've done any software development. There's the tangled nest of dependencies, that file that's in the middle of your system that everybody depends on and depends on everybody else. There's mismatched interface assumptions. Two components have different assumptions as to whether one is sending data, polling, event-based, the metadata, how information is represented, and so forth. And there's just weird design decisions that you see over and over in architecture. I took this picture myself. I didn't make this up. You can't make this stuff up. So there was a study from the SEI in 2015, I believe it was, where software practitioners, I think it was 1,800 software practitioners, were surveyed to assess the kinds of debt that they were dealing with and which kind of debt was causing them the most problem. And by far, they reported that design debt was the most pernicious, the most costly form of debt. So how do we detect this? How do we determine this? How do we put it on a scale? How do we measure the health of an architecture? And can this be automated? The answer is yes. I'll show you how. Can it be empirically justified and repeatable? Yes and yes. Well, you might say, isn't this a solved problem? There are technical debt detection tools like SonarQube and Designite out there already, Structure 101 and others. Sadly, no. We did a study which we published last year in the International Conference on Software Engineering, where we pointed a set of technical debt detection tools at the same set of projects and compared what it was they reported about those projects. And the bad news is that it was almost entirely idiosyncratic, which is to say the tools reported different things, even the most basic measures they disagreed on, like how many lines of code are in this file? What's the McCabe complexity of this file? They disagreed on those. Even worse than the fact that they disagreed, the files that they pointed out as most problematic, it turns out all they're pointing out is big files. Big files are bad. And you knew that already, and you didn't need an expensive tool to tell you that. And they're really not giving you more insight than that, sadly. And the problem is only getting worse. So existing tools, these tools primarily analyze static relationships. File A inherits from file B, file A calls file B, class A calls class B, aggregates class B, right? These are static relationships that you can determine from the syntactic relations you can determine by compiling or reverse engineering. But increasingly, our systems are dynamic. They're being built in more dynamic languages where these relationships are being created and bound at runtime. Our systems are being built as sets of services or microservices with dynamic binding between the relationships. And so if it's already hard to analyze traditional systems, with static relationships, it's even harder to analyze these dynamic and distributed systems. So let's look at the state of the art in design detection. And I'm going to be talking about the tool that has emerged from my research, which is called Deviate. We've got, actually, I need to update this slide. The empirical basis is now more than 500 open source projects and close to 100 industrial projects that we've analyzed. And what we do to analyze these projects is, first of all, we collect data from the project, not surprising. We look at the code, but we also look at things like the revision history and the issues and the issue tracking system. We then turn the analysis crank and we make some measures, and we identify the architectural flaws, the design problems that are causing design debt. And then we come up with cost calculations. How costly is this debt? After all, you might have a really horrible mess in one corner of your system, but it's not causing bugs and it's not changing. So don't mess with it. Don't trouble it. What we're looking for is the parts of the system that are both flawed and active. We sometimes call these active hotspots in architecture. So we do this automated analysis, we identify all this stuff, we show the results to the project, to the project manager, architect, senior developers, and we get their feedback. And sometimes we even convince them to refactor based on this information. So as I said, the data collection, what we collect is dependency information. This, a method in class A calls some method in class B, or class B inherits from class A, those kind of static dependencies. We collect history information primarily through the commit or revision history of a project. So we can tell in one commit, files A and B were committed together, and another commit, files B and C were committed together. These co-commit relationships often give you insight into dependencies between files, even if there's no structural relationship between them. A and B are committed together. There's something about those files that there's a relationship between them, even if it's not reflected in the syntax. And we collect issue information so that we understand the purpose of a commit. Was this to fix a bug? Was it to implement a feature? Was it to do a refactoring? We represent software as in a DSM. And presumably you guys are all familiar with DSMs. It's been used in the system engineering community since the 1960s, also used in project management. We're using it to represent software components and the relationships or interactions between them. But you can use a DSM, a design structure matrix, to represent any kinds of relationships between anything. So sometimes it's used to look at communication between people, or to look at information flows in complex enterprise architectures. We're using it, as I said, to look at software dependencies between classes or files in software. Once we've collected all this information, we, as I said, turn the crank. We run a set of automated analyses, and I'll describe those in a minute. Using this analysis, we can pinpoint the design flaws, and this is really where the magic happens. Design flaws are suboptimal design decisions or architectural decisions that are degrading the conceptual integrity of your architecture. They're making it harder to understand, to maintain, to modify the architecture, because you don't know when you make a change here if it's going to have an impact over here or here or here. And these design flaws, they tend to increase the coupling, decrease the cohesion of the system. And then we quantify all of this, which is really nice, because maybe you feel the pain of these design flaws, but maybe your boss doesn't. And so if you quantify it, you say, this is costing us X additional person months of effort every year, maybe then your boss will take notice. One way that we measure and monitor architectures is via metrics. So there are a couple of metrics that we measure decoupling level and propagation cost. And these are architecture-wide metrics where a single number is reflecting the complexity of your architecture, how tightly coupled it is. All other things being equal, you prefer a more decoupled metric. So I'll talk about the first of those, the decoupling level metric. We developed this in 2016, and we've done a lot of analyses. Here's an example of a cumulative distribution looking at 129 projects, 108 open source and 21 industrial. And you can see the red line here is the decoupling level line. And you can see that, oh, and I should say that the higher the number, the better. So the higher the number, the more decoupled the project is. And so over these 129 projects, you see an enormous range in the decoupling levels, from some projects that are horrible down at under 20%, which means basically you can't change anything without affecting some other parts of the system, to projects that are really nicely structured. So let's take an example. One project, this was an industrial project. Its decoupling level was 29%. That put it in the 10th percentile of our population of projects. And in discussions with the architects, it was confirmed that they had severe maintenance difficulty. The lead architect said that if they wanted to change one line of code in this project, they budgeted a person month of effort. No joke. The next kind of analysis that we do with DV8 is we identify architecture flaws, design flaws. And there are 6 kinds of design flaws that we can automatically identify: unstable interface, modularity violation, crossing, improper inheritance, clique, and package cycle. So I will talk about these, give you some examples in a minute, but I would just point out that these flaws matter, that they are highly correlated with bugs, changes, and churn. Churn is the number of lines of code that you need to commit when you're making a change or fixing a bug. So the more flawed your architecture is, the more bugs, changes, and churn you experience. And this is a very strong relationship. I'll show you in a minute. I'll show you the numbers. So let's just take a look at a couple of these. And again, we're representing software systems as DSMs. So here on the left, you see the names of files in a project. Each of the rows is numbered. You have the same numbers along the columns, so it's a square matrix. And each of the cells is annotated with information that indicates the dependency between the file on the row and the file on the column. So we see here DP, which means dependency. We see IH for inheritance. And then after those letters, we have a comma, and then we see a number. And the number represents the number of times that those files have co-changed in the project's revision history. So this gives us an idea of if that number is really high, these two files depend on each other somehow, even if it's not represented in a static relationship that we can reverse engineer. So an unstable interface. Why is this not? There we go. An unstable interface, we see this in this file 2, utils.fb utilities. If you look at column 2, this shows all of the files that FB utilities is related to, and you see that many files depend on it. That's the DP, and the co-change numbers are very high. So this is an influential file. Lots of other files depend on it, and lots of files co-change with it. And it changes very frequently. So this is clearly something suboptimal. You want interfaces to be stable so that when they change, the dependents don't change. And this file is not achieving that. Here's a second flaw type, which is called crossing. So in this case, we obscured the names of the files because this was a commercial project, but it doesn't matter. File number 5 in this DSM is both depends on and is depended on by many other files. So the column shows the files that it depends on, and the row shows the files that depend on it. And when we see a file that has lots of inbound dependencies and outbound dependencies, it shows up as a cross on a DSM. So that's why we call this flaw type crossing. There's modularity violation. So in a modularity violation, this again is another commercial project. We've obscured the file names, but what you see is there's relatively few dependencies that can be extracted by parsing the code base. So this looks like a nice DSM in the sense that it looks like there's not too many dependencies. I could change one file without altering the other files. However, when we include code change information that we've extracted from the revision history, we see a very different picture. This core set of files from file 7 to file 19 has tremendous numbers of code change relationships. So these files are changing together, even though there's no structural dependencies among any of them. There are some implicit dependencies. And so we call this a modularity violation, because those the causes of those files changing together are some shared assumptions or shared secrets. These are things that should have been modularized, but were not. And because they were not, every time you change file A, you also have to change file B. You haven't modularized that. You haven't extracted that dependency out into some abstract class, for example. So let's take a look at some real projects. This is from Apache Cassandra. Here you see I'm losing my words, an unstable interface in this first column. Over here, we see a cyclic dependency. So here we see an unstable interface. So for example, if you look at lines 13 and 14, cassandra.io.sstable and sstable reader. sstable reader inherits from sstable. sstable depends on sstable reader. That's a violation of object-oriented design principles. You should not have the parent class depending on the child class. So every project that we look at has design flaws. Every project has design flaws. So the question is, well, how much do they matter? Right? How bothersome is this? How much should I be worried about these design flaws? If you take Kazman's word for it, that every project has them, that means your project has them. Is this a problem? So we did a study asking this question. And the study, the question we posed in the study was, if a file is involved in more flaws, is it more error prone? Is it more change prone? So that's one way of asking whether the flaws matter. So for this study, we looked at 2, 4, 6, 8, 10 projects, I guess it is, 9 open source and 1 commercial. And we counted the architecture flaws. So we ran the automated analysis on these 10 projects. We calculated the flaws. And so we could determine for every file whether it was involved in a flawed relationship or not, or maybe several flawed relationships, because a file might be involved in a modularity violation and a cyclic dependency and an unhealthy inheritance. And then we also collected outcome data for each file. How many bugs have been reported where this file needed to be patched to resolve the bug? And what was the churn? How many lines of code were committed? How many changes have been made over the revision history to this file, and how many lines of code were committed for that? And what we see is a huge correlation. Now, you cannot read this chart, so let me zoom in on one project. This was Avro, another Apache project. We like Apache because they tend to have big, widely, heavily used and heavily modified open source projects. They're used by everyone in the world, and they have good practices. They collect the data that we need to analyze. So what we see here on the rows is the set of files that had no flaw, the set of files that had one flaw, 2, 3, and 4 flaws. So we simply calculate the flaws and the bugs and changes and churn for every file in each project, and then we group them into sets. So for the set of files in Avro that did not participate in any design flaw, those files had on average 0.1 bugs, requiring on average 3.7 lines of code to resolve. They had on average 0.1 changes, requiring 29 lines of code. Now we look at the set of files that participated in one design flaw, and not too bad. 0.4 bugs, requiring 3.9 lines of code, 0.9 changes, requiring 26.2 lines of code. But as soon as you go down to the higher levels of flawed relationships, you see dramatic increases in the bugginess of those files and the change proneness of those files. So the bottom number here is the correlation, the Pearson correlation coefficient. We're looking at what's the correlation between the number of flaws and the number of bugs, changes, and churn. And for every project that we studied, that number is typically around 0.9, a very high correlation. In fact, it looks like causal. And we've done some other analyses that have shown that. So we did another study based on this. We thought that was interesting. I wonder if this applies to all kinds of bugs. So we looked specifically at security bugs. We did essentially the same analysis, but instead of looking at all bugs, we just focused on security bugs, their frequency, and the frequency of changes made to implement a security feature or resolve a security bug. And so we had to look at projects that label their bugs as being security related or not, but we found a nice set of projects, 11 projects in this case. And again, in each case, the correlation is very high, typically around 0.9 on average. So we see in this second column, the correlation between all bugs and flaws. And here we see the correlation between security bugs and flaws. And so this should make you worried, right? Even if you say, well, bugs are bugs, we always have to deal with them. Security bugs are especially pernicious, right? These can bring down your system, bring down your reputation. So the design flaws really matter. We can also quantify the cost of each of these flaws and the sets of files that contain these flaws. And based on this, we can calculate the return on investment that you can expect to enjoy if you fix the flaws. So the reasoning here is, if you believe in the correlation data, if you believe that flaws actually cause greater numbers of bugs, changes, and churn. As I say, we've actually done a causal analysis and showed that that is, in fact, the case. These are causal. Then if you remove the cause, you should reduce the bugginess and change proneness of those files, right? You go in, you remove the tumor, the patient should be healthy. So the question is, well, how much benefit will I gain if I go and I invest that money, I spend that money on refactoring? So we did an analysis with an industrial partner. This was with SoftServe. They're an international outsourcing company. And we looked at one of the projects. Again, we could not use the actual file names here. So the file names are all replaced with fruits and vegetables. And what we did is we found the most flawed clusters of files within that project. And we looked at how many bugs, how many changes were these experiencing on an annual basis. And we calculated the number of defects in each of those clusters of files, the number of changes, and the lines of code required to fix those bugs and implement those changes, because lines of code translate to effort, right? So that was our measure of effort, was lines of code. We then asked the architects to calculate a refactoring plan. Knowing the flaws, you can figure out what you need to do to refactor. If there's an improper inheritance, typically what you need to do is move some functionality from a child class up to a parent class. If there's a cyclic dependency, you need to break the cycle of dependencies. If there is a modularity violation, you need to modularize those shared secrets. So once we identified the design flaws, we could say it's these 6 files, this is the flawed relationship. What would it require for you to refactor that to remove the flawed relationship? And so they came up with an estimate of 14 person months of effort to do this refactoring. We then looked at the expected number of defects, changes, and lines of code for these files if they were refactored. And the assumption here is that if you remove the tumor, the patient goes back to being healthy. These files would then go back to being average files in the project. So the expected values were based on project averages of bugginess, change proneness, and churn. Given that, we could calculate the amount of effort that would be expected to be saved by doing this refactoring, by taking the number of lines of code that you don't have to write because you've removed the design flaws. We calculated that they would save 41.35 person months of effort in the first year alone. This would require 14 person months of effort. It's a 300% ROI in the first year alone. That's data that you can take to your manager and argue for a refactoring. The normal argument for refactoring is really weak, right? You go to your manager and you'd say, my project is a mess, I'd like to refactor. Your manager is going to say, well, how many new features is that going to give me? And you say, none, it's refactoring. And the manager says, go back and do your job, right? Don't bother me. And that's because you can't make this cost-benefit argument. You can't say, by refactoring, I will increase velocity, I will reduce bugs, I will reduce the amount of time to implement a feature or to fix a bug. And I'll show that in a couple minutes with a case study. We've done a lot of case study and action research with industrial projects. So this was some work that we did in 2017, 2018 with ABB. We analyzed 8 of their projects. These are all embedded software systems. And these projects were being developed at multiple locations. They differed in age, domain, and size. We did this analysis. We reported the results back to the architects and collected feedback. All 8 of the projects verified that this information was useful and insightful with them. 6 of the 8 projects immediately began refactoring based on these recommendations. And they said that the results gave them numbers, gave these quantifiable results where they could judge their projects compared to other projects. They could figure out how much penalty they were paying by the architecture degradation. And one of the projects, the project with the lowest DL score, the one that I alluded to earlier with the DL of 29%, is undergoing a major rewrite. We also worked with Huawei Can't work with them anymore, but this was a number of years ago before they were bad boys. And we helped them adopt these architecture measures based on DL and architecture flaws as a corporate standard, which they then used in over 100 projects. They quantified their architecture debt, and they found a positive correlation between these measures and the productivity of those projects in 24 out of the 29 projects. If you have a small project, debt may be manageable. You may be able to continue to be productive despite having debt. But the larger and more complex the project is, the more that's untenable. The third industrial study that I'll talk about is with a Canadian company, Bright Squid. This is a company that develops secure communication platforms for the healthcare industry. And we took about a 1-year sample of their project history, and we analyzed it. We, of course, identified the architecture debt in this snapshot of the system. We call this the before state. And like with SoftServe, we recommended a refactoring plan based on removing the flaws that we identified. And they agreed to do the refactoring. So they did the refactoring over a 3-month period in 2018. And then we measured the after state. So we wanted to have a comparison of the before and after state, both in terms of structure, how well we did at removing flaws, but also in terms of the outcomes. Did productivity improve as a result? So what you can see here is that, in fact, the number of flaws did go down. So the number of cliques before was 17, after it was 10. The number of unhealthy inheritance went from 60 to 30. The number of unstable interface went from 12 to 8, and so forth. So they did, in fact, succeed in removing the flaws. This refactoring took them, you can see here, about 14 person weeks of effort. They shrunk the code base, so they identified a lot of redundant files, so that was good. And importantly, what they found is after the refactoring, the time needed to close issues was reduced by 72%. The amount of the number of lines of code that they implemented to fix a bug dropped by 2/3, from 102 to 34 before and after the refactoring. And the amount of time it took to identify and fix bugs dropped by 30%, from 10 to 7 days on average. So this was a huge win for Bright Squid. Okay, almost done my talk. So what have we learned? There is enormous debt in software today. Yes, in your software. It's rare that we found a project that was certainly a large, long-lived, complex project that was not heavily burdened by debt. And that's the bad news. The good news is we can do something about it. It can be fixed. It can be paid back. And it's possible to automatically assess the debt and quantify the debt and use this information to actually increase your velocity. So it's possible to bridge the gap between management and developers. And this is something that had previously been very difficult. And certainly we've seen this over and over again in our industrial interactions. And we have more than the ones that I've presented here, but only have so much time for this talk. So most of the projects that we have analyzed have embarked on major refactorings. We gave them the bad news, we gave them the good news, and they decided that refactoring was worthwhile. And a number of companies are actually using this now in their development process, in their nightly builds or review process. So final thoughts. Yes, you can increase your development velocity. You can't manage it if you don't measure it, though. That was the guy rowing the boat, right? He had no way to measure how bad life was, and so he was just working hard. Quantification is key for this. And it needs to be automated. if it's not automated, it won't be done, or it won't be done regularly. And that's why, as I said, I blame myself. The techniques that I had developed earlier in my career were heavily human-centric and therefore expensive and not regularly done. And so this is something that you can build in as a kind of architecture lint into your build or deployment process. And this leads to improved architectures. So with that, I'm happy to take questions. I think the slides are going to be shared with people. There's a long list of references here if you're masochistic and want to read a lot of academic papers, then happy to provide these for you. But for now, I can take questions. Okay, well, I can answer the first one in the chat right away. So Jeff asking, your ROI analysis appears to be saving future effort that may not have funding or schedule. Yeah, that's exactly the point, that this is essentially predicting areas of future effort. The areas that are flawed are going to cost you more, have more bugs and more changes in the future. And without making a case for refactoring, this will not be allocated funding. So that's part of the purpose of doing this analysis, is to convince the money people to allocate time and budget to refactoring, because in the end, it is in their own best interest. I like medical analogies. And so I mentioned, removing the tumor, right? If you don't have the CAT scan or the MRI, you don't even know that the tumor's there. And so you're never going to remove it. This is the CAT scan. And it's identifying the problem. And then it's up to you to decide what intervention you can do or want to do. And this also helps you provide the business case in terms of dollars and cents to the money people. What tools do you use was the next question from Dawn. The tool is called Deviate. I put a link in the slide, but it probably went by really fast. A colleague of mine has commercialized this technology that we've been working on for more than a decade. So I can put it in the chat. Her company is archdia.com, ARCHDIA, for architecture diagnosis, I think is what the acronym stands for. What are the main drivers for technical architecture debt management, attention, skill? So why do we accumulate debt? And the reason we accumulate debt is a focus, almost singular focus, on implementing features. No developer ever wakes up in the morning and says, I think I will degrade the code base today. I think I will introduce debt, right? I'm assuming that most developers are sincere and they just want to do their job the best way that they can. But design debt gets introduced nonetheless, because people don't understand the consequences of the dependencies that they're making when they make a call between class A and class B. They don't understand how they're degrading the debt because they don't have the insight. Architecture is largely invisible. And so it is developers who introduce debt unwittingly, unintentionally, but it is, I've never seen it otherwise, that architectures always degrade over time. They get worse over time. So I'm interested in learning about concrete techniques for modeling software architectures. Is UML, SysML the future of software architecture? Probably not. In my experience with working with industry, unless companies are working in a safety critical domain, they do little to no modeling. Very few companies that I've dealt with make serious use of UML or SysML unless they're in some safety critical domain. let's see, another question. Have the results of Deviate been compared to its competitors? Yes. So the study that I mentioned near the beginning, where we looked at technical debt detection tools, and I said Structure 101 and Designate and SonarQube really don't give you any insight beyond big files are bad. We also analyzed Deviate in that analysis, and Deviate was in fact the only tool that provided insight more than big files are bad. So yeah, it actually did stand out from those other tools. I can somewhere here, yeah, I can put that paper in the chat. There we go. How many bugs are typically introduced by refactoring? How can these bugs be quantified? I don't have those numbers. For sure, bugs are introduced when refactoring, but it's typically a short-term phenomenon. So it's something that you introduce bugs when you refactor. You get a near-term blip for the first week or month or couple of months, and then things get better after that. So there is a cost to be paid for refactoring in terms of the effort that you make and short-term effort on swatting bugs. But the benefits of having the refactored architecture far outweigh those costs. I don't have the numbers at the tip of my tongue. Can these statistics also be used for embedded systems? Yeah, in fact, so many of the companies that we've been working with, like ABB, like Huawei, like Samsung, are building embedded systems. That's their, 98% of the software that they produce is for embedded systems. And embedded systems, in many cases, have very long lifetimes. So in ABB, some of those systems were 20 or 30 years old, and that was why their architecture debt problems were particularly severe, as they had been accumulating debt for decades and had no consistent program for measuring, monitoring, or paying down this debt. And it was just weighing them down. I mean, think about it. One line of code, you have to budget a person month of effort. Like, what project can make progress with that kind of terrible complexity that they're dealing with? And it was that way because nobody knew the implications of changing that line of code. It might affect some timing behavior or some memory behavior or something that's very subtle and not represented anywhere explicitly in the architecture. So yeah, I don't know if embedded systems are in general worse than non-embedded systems, but certainly the experiences that we've had with them have been that there is significant debt in them, in part just because of their age.
Okay, thank you.
So I think I've answered the questions in the spreadsheet, because many of the questions have already been covered, or people are just indicating their interest. Oh, here's another question. Let's see. After refactoring, how can architecture degradation be avoided in the future? Should architects be checking more frequently? Why is a developer sprint allowed to be completed if their work is degrading the architecture? Those are fantastic questions. And again, I will say right now that is the norm, that architectures do degrade, that they are not checked at all, and sprints are completed because no one has, or are approved because no one has insight into the architecture degradation. It's not part of, it doesn't get caught typically in code reviews. And so this is why we've been recommending building this kind of checking into the build process, into the nightly build or the commit process, something like that. So as an architect, I would like to know, if I approve this commit, is it going to degrade the architecture in some fashion? And I can get a report that says, oh, this commit is going to introduce one new architecture flaw. And then I can make a decision. Is it worth it? Maybe I'll put that on the backlog to remove that later on. Maybe I'll say, no, you can't do that. You have to abstract that bit of functionality. You have to refactor that inheritance hierarchy. You have to undo this cyclic dependency before I'm going to approve that commit. So yeah, without having visibility into it, it's really difficult to avoid these architecture flaws being introduced into the architecture. So if you do have visibility, at least you can make a conscious choice as an architect as to whether you're going to allow this to happen or not. Sorry, I got to plug in my computer. I'm getting low on battery here. Okay, back. Let's see, there appears to be a gap. The point of this work is predicated on a gap involving multiple upstream opportunities directly related to commercial versus government projects, business regulatory requirements, and we are paying you all this dollars, pounds, euros. You said you are the best and have done things like this in the past. Why are you making all these mistakes? Yeah, so right now, how is software judged? How do we judge software? And it's a couple things. One is, if you're a manager, you are primarily judging your developers on their velocity. How many commits did you make last week? How many features have you implemented in the last year? And while it's important, clearly, I mean, the software doesn't exist for its own sake. It exists to deliver some value to its stakeholders. If you ignore this other dimension, this dimension of increasing complexity, you pay for it eventually, right? If I ignore the fact that my cholesterol is 300, eventually I'm going to have a heart attack. And, you know, I can happily go on eating my cheeseburgers and fries for a long, long time, but eventually, probably, it's going to bite me. It's going to, you know, result in some really bad outcome. But if I'm not measuring my cholesterol, I don't have insight. I'm just happily eating my cheeseburgers. So it's a measurement problem. It's a visibility. It's an awareness problem that right now, very few projects pay attention to architecture quality. They might pay attention to code quality because there are code checking tools, but that simply has nothing to say, does not analyze the architectural flaws, the architectural quality of a code base. And again, going back to that SEI study, the respondents said that architecture debt was by far their most costly, their most pernicious form of debt. And so it's not really being addressed in any widespread way in any industry, actually, in any company that I've been involved with. Could this be alleviated by requiring software systems engineering approval of the sprint stories? Requiring software systems engineering approval? Well, yes, but only if the approvers have insight, right? So again, without the right diagnostics, the approvers don't know what's going on. Right? It would be like your doctor not having access to X-rays, MRIs, blood tests. They would be really hamstrung in terms of what kinds of diagnoses they could make, and therefore what kinds of therapies or remediations they could propose. So the visibility into the problem is what is currently lacking from most architects or project managers' toolboxes. And that's what my research is trying to address. So let's say, does a 12-factor cloud native microservice-based architecture bode better than traditional software designs for architecture? So there's been a lot of buzz about microservice architectures in the last 5 years in particular. And the belief was that microservice architectures alleviate many of the problems of traditional architectures because microservices are micro. And so you tend not to have these big blobs of code. You have little more conceptually tractable chunks, microservices, that interact with these other microservices. That sounds great. What has happened in practice, certainly in the studies that we've done with companies like eBay, Comcast, other companies that we've analyzed their microservice architectures, is that they have microservice spaghetti, which is to say they just have ever increasing numbers of microservices with ever increasing dependencies. They have all kinds of redundancies in them. So microservices that are almost but not quite the same as each other. They have dynamic dependencies, which are really difficult to spot and really difficult to debug. And so microservices help because they encourage more modularity. They encourage you to build smaller units with explicit interfaces. That's good, but they are not a panacea. You can have microservice architecture hell, just like you can have regular architecture hell, because of the dependencies, the many blossoming dependencies between the microservices, and the fact that many of those dependencies are implicit, not explicit, or can only be determined at runtime. So that can make analyzing, debugging these microservice architectures really difficult. It can make having a sensible evolutionary plan really difficult. So yeah, microservices have some benefits. They're not a panacea. So I think that was the last question. Did I miss anything? People, you can unmute yourself if you have more questions that I somehow skipped over.
Okay. No, I maybe have one, and this is because this is something I always predicate, and maybe I am completely wrong. I deal a lot with bad architectures myself, and I always say the only two measurements that you really have to keep an eye on and get to grip on is your coupling, so loose coupling, and your functional cohesion within your container or module sizes. What would you say to that?
You were spot on. And
thank you.
These flaws, you can, if you look at how they're defined, really all of them are manifestations of either improper coupling or improper cohesion. They're just different ways in which bad coupling and cohesion decisions are manifested in the software designs that emerge.
Okay,
so, yeah, you're exactly right. But my guess is you don't have good enough tools to precisely measure that bad coupling and bad cohesion.
Yeah, I use a software called TeamScale, but it was developed by it's quite similar to Deviate. It also tracks about over history, and you can also track architecture violations if you have defined your architecture upfront. But another one is that I always preach is that people, or especially developers and architects, should really know design patterns, because it just really helps you with communicating. What is your opinion to that?
You were right. And actually, my next book is going to be a book on design and how trying to help educators teach design and design patterns better. because right now it's not being done very well in our universities, and you know, I share the blame in that. That's been my field for the last couple decades. We ran a study a few years ago on the use of design patterns. So we had 3 different universities participate in this study, and we taught the students architecture and design patterns for a whole semester. At the end of the semester, we gave them a final project which used the design patterns that they had been taught. We gave them a UML specification, a description of the system that they had to implement. They all implemented it correctly. It passed the test. The functionality worked. 78% of the students violated the architecture in a way that undermined the intent of the design pattern. 78%, right? So yeah, design patterns are great, but only if they're faithfully implemented. And students didn't realize that they were undermining the design patterns. So I still think tooling is needed. People simply aren't aware of the suboptimal architectural decisions that they're making at the code level, because design isn't obvious at the code level.
Okay, thank you.
Welcome. Okay. Well, thanks to everyone for their attention. And I think you have my contact info. Feel free to shoot me an email if you have more questions.